Okay. So a graphical approach. So week 5. So our focus is we're going to finish talking about inverse functions. We're going to graph these inverse functions essentially. And then we're going to talk about like increasing and decreasing functions. And that will finish chapter 1. And then we're having the test number 1. Unfortunately, I can't make it on Thanksgiving. So it's going to be on October 18th, which is the Monday, which I announced. So you have lots of time to basically study, catch up if you're falling behind, etc. And there's assistance and help. That's what, so on test number 1 will just be chapters 0 and 1, not chapter 2, but I'm going to continue teaching the curriculum moving forward. So we still have to finish up. So the domain and range of an inverse function. So we're looking at functions that are one-to-one. Why are we looking at functions that are one-to-one? Can anyone tell me? Because, yes? Right, yeah, because in order to find the inverse function has to be one-to-one. Exactly, perfect. That's the answer I was looking for. So it needs to be one-to-one because only one-to-one functions have inverses, essentially. And then remember this definition, like the inverse function is equal to x. And this was our input. And this essentially means, what does it mean? It means f of x is equal to y. So they're the same thing. Now we're considering like these one-to-one functions. So the inverse function is defined precisely when y is in the range of f. So therefore, the domain of the inverse equals the range of f. I'll just write it. So this just means the domain, just so we remember, of the inverse function is basically the range. And it's similar to what I drew in the seminar, like a little picture of a mapping of, we go from one set x to y with the function, and then the inverse goes from y to x. So like the domain and the range are sort of like switched for the inverse. So you should be able to see that then the range of the inverse equals the domain of f. And kind of can think about it and draw yourself a little sketch as to why, like they kind of like switch. So the takeaway here is the domain and range of an inverse function. If f is a one-to-one function, then the domain of the inverse equals the range of the function, and the range of the inverse equals the domain of the function. So we're going to see an example of this using a graph in this example. So suppose we have this function, f equals 2x plus 3, on a particular domain 1 to 3. So we can sketch it. So sketch this graph. So let's kind of I'm trying my best to draw straighter lines. Okay. Now the domain goes from 1 to 3. So that's going to be on our x-axis, and our y is here. We could start thinking of just points to plug in the endpoints, and we notice that this is a linear function because it's going to be a straight line, which I'll talk about linear functions. So when x equals to, let's label it. And this was good. I noticed that the quizzes, people kind of like drew like really small pictures instead of like, for example, if you take a photo of a person, you want to zoom in on their face, right? Or zoom in on the picture. Yeah. So the important details were kind of squished very small, like people didn't zoom in properly when doing the quizzes. So try to think of the endpoints and the most important parts when kind of graphing. So here the domain is 1 to 3. So we could just calculate those. Oops. And we would see at like these endpoints, what happens? Well, 3 times 2 is 6 plus 3 is 9. So now we know kind of like the endpoint, so we can visualize what's important. Do we need to zoom in? Do we need to zoom out? How should we scale this? So we can do 1, 2, 3, 4, 5, 7, 8, 9. Okay, so it goes from 1 to 3 here, and that is our domain. And then it goes 1, 2, 3, 4, 5, 6, 7, 8, 9. So at 1, we have 0.5, and at 3, we have 9. And we can draw a straight line. We could take a number 2 in here as well, like 2 times 2 is 4, plus 3, 5, 6, 7, so 7 in here. And just connect that with a nice straight line. So this would be our range. As you can see. Now, it passes the horizontal line test. So let's just make a little note. So like this function, f of x equals 2x plus 3. On this particular domain, uh, 1 to 3, is a one-to-one function. So it does have an inverse, is the point. And we can see by the sketch, if this was the domain, which is basically our inputs, our outputs here, the range, another word for it, it goes from then, therefore, 5 to 9. Check mark. Okay. Now that, so like, let's find the inverse. So of this function, of the same function. So to find the inverse, again, we just do y. So our f of x is equal to y, and our f of x is equal to 2x plus 3. So we can subtract 3 from both sides. So y minus 3 equals basically 2x plus 3 minus 3. This goes to 0. And then we can divide by 2. These cancel, so you get x equals y minus 3 divided by 2. Okay. So then the inverse is going to be y minus 3 divided by 2. And if you wish, you could change the variable name, because sometimes you don't want the input variables to be y, like to call them. You want, so let's change. It's just a name convention. So we obtain the inverse, x minus 3 divided by 2. And this is the inverse function, of course. So again, what we did is basically we isolated for x here. And we solved. Okay. So let's sketch the inverse function. Really trying to work on my graphing skills using this tablet. Trying to get better. So the inverse of this function, suppose we like plotted some points here. Well, before we get to here, we could use the theorem to find the domain and range of the inverse function. So what is the domain going to be? Yes, exactly. So the domain of the inverse, right, I heard it, was 5 and 9. And it can help us plot this better. And the range of the inverse, what is that going to be?
1 and 3.
Right, 1 and 3. And they are equal. What else? So the domain is actually equal to the range, as you notice, of the function of f. And the range of the inverse is actually equal to the domain of the function. Okay. So it helps us sort of like plot them. So now we can see that if we take the domain of the inverse, some points, and we know that it's now going to be 1 to 1, etc., of this function. Remember, the inverse function was this. So let's plot them. So like, let's take the endpoints. It's usually a good idea. And then some numbers in the middle sometimes is also a good idea. So 5 minus 3 divided by 2, get 1. Maybe another point in the middle, 7. So 7 minus 3 divided by 2 is 4, so 2. And the inverse of, let's say, 9. So 1, 2, 3. Okay, so then we can again plot this. So we could plot, let's say, 5 over here, 9, and 1 and 3. So it's going to look like that. Okay. So what about graphing approach to inverse functions? Like, did we notice a pattern? So from like the examples that we previously have done, can you observe anything interesting? Do you see any patterns? Mathematics is the study of sort of finding patterns and discovering things like this. So what patterns do you see when we plot these things? So let's replot it, the previous. Try to draw it a little bit more carefully. I'm going to sketch this time. I hope so. So a 1, 2. So the function was first this one, 2x plus 3. On the domain, just so we remember, the domain was 1 to 3. So when x equals 1, so 1 times 2, 2, 3, 4, 5, we get 5 here. And 3 was at the 9. So nice straight line. Now the inverse function, just to remember, was we interchanged and we found that the inverse was equal to this. And the domain here was 5 and 9. And the range was 1 and 3. Okay. So what kind of pattern do you see? Anyone? Yes? Exactly, but like, what is it rotated on? This. Right. And what is this line called? It's called y equals x. So that line, it looks like it's kind of reflected along the y equals x axis. So the inverse is reflected along the y equals x axis. Sort of if you project like this point down to this axis, this distance, and this distance, they're the same. Same here. Same here. If I drew it well, you can imagine this is true. I think. It's a little, I didn't draw it perfectly, but you get the idea. It's reflected. Okay. So what about like this function? Consider this function x squared plus 2 on this positive domain. Draw its graph, and what does this graph of the inverse look like? So let's again draw the graph. So it moves up, it transforms x squared up 1 unit. So it begins here. And so when x equals 0, this is 1. When x equals 2, or when x equals 1, let's say, here, what happens? So 1 squared, 1 plus 1 is 2. So it's something like this. So this is f of equals x squared plus 1. And I don't have to worry about what happens over here because x is non-negative. Just on the positive or greater than equal to 0 domain. So, but what about the inverse? So, okay, we can draw that, but what does the inverse look like? So it's a little bit more complex. So the inverse of this function, how do we find it? So we set y equals to x squared plus 1, and we solve again for x. So this implies we bring, so we're going to isolate for x. So we bring the 1 over. So we get y minus 1 equals x squared. And then we take the square root of both sides to get rid of the square here that we don't want, which implies square root y minus 1 equals x plus or minus, right? But because the domain is greater than or equal to 0, x is basically non-negative, we don't have to worry about like these negative values. So you don't have to worry about that because of this. So then we could interchange x and y. And then we get the inverse of this function is equal to the square root of x minus 1. Okay, so now we can plot this function on this graph. I'm just going to erase it and write it in a different color. You don't have to erase it. Okay. So you can think of it like a little table of values. When x is 0, well, that's not defined. Okay. So when x equals 1, 1 minus 1 is 0, square root of 0 is 0. So here's your first point. 2 minus 1 is 1. Take the square root of 1 is 1. So that's your next point. And then you could do some more points if you wish, and connect the dots. It's something like this. Okay. As you can see, well, this is our inverse. Let's just mark it. And it looks like, again, it's symmetric. Oops. Along this axis of y equals x. So again, in this case, our function, our inverse function is symmetrical along the y equals x axis. So, and this is essentially what this little note down here is basically saying. You can consider arbitrarily points along this function, for example, 1, 2, this point. So the inverse to, when you plug in 2, is going to be 1. So the point 2, 1 is along this inverse function. This is by the definition that we have of the inverse function, y equals x, just means, again, f of x is equal to y. So it's just that flipping. So there's nothing especially special about our choice of a point. So basically the same property holds. A point AB on the graph of a one-to-one function, if and only if this point BA is on the graph of essentially the inverse function. So you just like flip the points essentially, and that will be on its inverse function. Let's just put it in a box so you remember. So it basically suggests an easy way to find the inverse of the function from the graph of the function. So the graph of a one-to-one function and the graph of its inverse are this keyword, symmetric, about this line, y equals x. And each graph can be obtained from the other by flipping it along this y equals x axis. So another example would be just the graph. Let's just draw a quick one. Graph of, let's say, the function f of x equals just x plus 1. Well, we just move it up 1 unit. We know it's going to be like this. So the y equals x axis, when x equals 1, y equals 1, when x equals 2, y equals 2, so on. It's just this guy. So then we can easily find the inverse. Will be here. Oops. This is the inverse. So the graph of the inverse is simply just so we can find it, let's say it's found. Simply by flipping it. The graph of just of f of x around this line, y equals x. That's it. So it's actually extremely useful when dealing with functions whose inverse is very difficult to determine. We might not always be able to find a rule for the inverse, but you can draw its graph essentially. So that's the idea, is to always be able to draw the graph if you know what it is. So it's an easy way to kind of like deal with functions and finding the inverses. So for example, let's say we have something like this. And we have like that. You could just simply draw the line. Oops. Maybe I didn't draw it. So you can draw that line, y equals x. And then, of course, we just have the same distance on this side. Maybe again, it's not perfectly drawn. So just try to draw these as any graph here. So kind of like it goes off the sheet, but the idea is this distance here to here, and from here to here, the right angles. So this distance and this distance are the same. This high distance to projected to this part here, they're the same. So I put two lines to indicate they're the same, etc. So those distances are basically the same. So there's that symmetry along the y equals x axis. I think a picture says 1,000 words, so it's easier to visualize it with pictures. So increasing and decreasing functions. And you do use this a lot in calculus, I won't lie, increasing and decreasing functions. So a function is called increasing on an interval if, so suppose you have let's do an example over here of increasing. So we can draw a little sketch, like let's say like this. So whenever A is less than B, and we have an interval, if f of A is less than f of B, this is said to be increasing, something like that. It could be curved, it could be whatever, but it's increasing. Decreasing, of course, let's draw a little sketch. So again, whenever A is less than B, but here, f of A is greater than f of B. So it could go down, as long as it goes down in some way. And this is going up in some way, as A goes towards B, and A is less than B. And it's on an interval. So this is going negative way, this is going positive. Let's go like that. Put a little star beside it. Make sure you know that. So given below is, I'm going to draw a graph. Lots of graphs today. And we're going to find where is it increasing, decreasing. On a domain, let's say from -2 to 6. So 1, 2. Let's say it goes up to 3. Here's 4. So let's say we have a function that goes from -2, or no, let's say 1 to 3, drops down. Say something like this. Okay. So suppose like we have a function like this. Hopefully you can see it. And so we have kind of like intervals. We can try to find the intervals where the function is increasing and decreasing, etc. So I like to kind of section it off just so I can see it a little bit clearer with like these dotted lines. So where is this interval? What is the interval where this function is increasing? So what are those x values essentially? So yes? Right. -2 to increases to here. Yeah, 0.
If there's no point there, or do we make our own point there?
Yeah, because imagine you're like walking up a hill, right? So you're here, you're walking up the hill, you're at the top of the hill at here. Even if there's no point, but like that's still the top of the hill.
Yeah, but if you're like the whole thing is an increasing value from one point to the next, right?
From here to here. So I'm walking up a hill, and up here, I'm at the top of the hill. And then I start to come down the hill.
Yeah, but let's say the end of the top of the hill or the bottom of that second hill is still higher than the beginning of the first hill from 1 point.
Oh, did I not draw this? You're saying this is higher?
No, he's saying 0.1 is like,
Like 0.1
we define two.
has an increasing value. But if the increasing value is decreasing from the middle between 0.1 and 0.2, are we supposed to put our own? point
Yeah.
in that?
Then from here to here, it increases again.
Yes.
Yeah, and then here to here, it increases.
Yeah, no, I know what you're getting at. I think the problem is you defined the first interval there as -2 to 1. And so that's that first interval you defined. So you never made a point at 0.
Oh, okay.
And so I think the confusion is that do you make a point at 0?
Yeah, you would make a point here.
Okay.
Sorry.
Sorry, and I'm not like the best drawer like here. But yes, right? So you would have to like just add a point there or something like that. Like you have to make it where it makes sense. And relate it to something that you might know. Well, you can relate it more to. That's what I was trying to say about the hill idea. Even like, is there a point? Like the points are kind of arbitrary. They're just like one little speck. But essentially,
When you say intervals, you mean we have to basically make our own points. on
Yeah.
the chart.
yeah, it's a bit creative here, right? Like it's almost like art class. But you walk, like you start at this point, you go to here. So it'd be like 0, but then you come down, so then it's decreasing. So we don't have to think about the point necessarily. Don't worry about what's happening at the endpoints per se. But then we come down, so let's include it. You could say the point is neither, but so you come down to here. Then you start increasing again. All the way to 2, or no, all the way to 3. But then from 3 to 4, let's say you're walking along it, you're a person. Here, walking, or walking flat. So you're not increasing or decreasing, you're staying constant. And then you're walking down. So you're walking downhill. So you're decreasing. And then you're walking back up. Okay. So we're just looking at the X values. Does that make sense? Yeah. And it's like important for physics applications, like you're increasing, like versus like distance versus time graph, connecting that to something that you know. So you go up, you see here it's flat, the slope is flat. And then you start to come down. I drew that a little bit nicer. It looks a little high, but isn't my intention. But that's the idea. So just to make sure that you understand the idea of increasing. So some intervals increase, decrease, or neither. They don't increase or decrease. Don't, again, worry about the endpoints per se, but worry about the general idea. So some functions show the same behavior on the entire domain. So instead of an interval, the whole domain. And so a function is said to be increasing if the function f of a is less than f of b whenever A is less than B, and A and B are in this domain of F. So it essentially gets quick little sketch. It gets larger and larger and larger. A function is, so this is increasing. A function is said, of course, to be decreasing of the opposite. So if f of A is greater than f of B, whenever A is less than B. So this would be, of course, decreasing. So if f is an increasing function or a decreasing function, then I can never have two or more x values with the same y value. Why is this? Well, we could draw, of course, again, like a little sketch to convince us. Just anything increasing. And so by that horizontal line test, every increasing function is there going to be 1 to 1. So all these are one, so they pass this horizontal line test. So the idea is, and then we could of course draw it for decreasing. So like, let's say you pick 2 points. It's going to pass that horizontal line test. So this decreasing function is therefore 1 to 1. So what does this mean? So if f is increasing, or decreasing, everywhere. So on the entire domain, everywhere. This implies, of course, then f is a 1 to 1 function. So if it's a 1 to 1 function, what does this imply? And therefore it has an inverse, right? This, and has an inverse. Okay. So then, so these increasing, decreasing functions everywhere have inverses. And you can just draw a little sketch to understand it more deeply. So like they essentially, they have an inverse. So however, if a function has an inverse, this function must be 1 to 1. We cannot always conclude that if f is increasing or decreasing, that it's always this way. So fine, hold on 1 second. So let's read. So if a function has an inverse, this function must be 1 to 1. But can you conclude of something that it's increasing, that it's 1 to 1, but it's not increasing or decreasing, or everywhere? Let's just draw like a little sketch. So let me write this out a little bit more clearly. So find an example of a function that is basically it's 1 to 1 we're looking for. So it's going to pass basically the horizontal line test. So something that passes it. However, it's not increasing or decreasing everywhere. So let's find an example. So drawing a little picture or sketch. Let's say something increases from here to here. And then from, let's say over here, it decreases like that. Well, as you can see, this does pass that horizontal line test, check mark, right? So this passes the horizontal line test. So it is 1-to-1. So but it doesn't increase or decrease everywhere. So this is just a counter example. Okay, chapter 2. So essentially, we're talking about linear, quadratic, polynomials, and rational functions. So this is something that we use very frequently in mathematics. So far, we deal with, in this course, I fall into one of these categories. And then we'll be talking about trigonometric functions later. So basically, informally, what is this? So a linear function is just simply you probably know this intuitively, just a function whose graph is a line. So that's what we're first going to be talking about. So lines and linear functions. So the slope of a line tells us how y changes when x changes. So how can we determine if two lines are parallel, and what does this mean? So let's draw a little sketch. And we use this very frequently. So let's say, suppose we have a nice straight line. We have a point here. One here. So as x changes along this x-axis, this is the change essentially in our x. Here is their change in our y. What else is this? You know, it's basically rise over run is the slope from high school, right? So what does this change mean? So the slope is very important, a concept, slope, even in artificial intelligence and things like that. they use derivatives, they use slopes, they use these things. So the slope of a line is a measure. They use this in economics to determine how fast things change. So the slope of a line is basically a measure of how quickly y changes with respect to x. To a change in x. So essentially, the steepness or the flatness, it tells you how fast whatever you're looking at changes. X and y are here arbitrary variables, but they can represent different things. X can represent time. Y can represent prices. How fast are prices increasing? What is happening? Things like that, which relates to the financial world and what's happening, trying to relate it. Okay. So the slope, suppose you have 2 points, x1, y1, and x2, y2. They're just basically any 2 points on this line where x1 does not equal to x2. Then the slope m of the line is given by this formula. So again, let's write this down. So the slope is equal to the change in y over the change in x so the change in y is just going to be y2 minus y1, because that's that difference. Subtract x2 minus x1. And we can draw a little sketch to remember this. So you have a point here. So let's say this point is x1, y1. We have another point here. This is x2, y2. Can draw a little triangle. There we go. So as you can see, the change in x is just going to be this point x2. This is your x2 point minus your x1 point. And then change in y just the y2 minus the y1. Again, this m represents slope. So any line can be uniquely determined by its slope in a point on the line. So essentially, if you have, let's say, point here, and then we have, let's say, other lines. And let's say these are other lines with slopes equal to 1. Like you see that they're parallel to like this particular point and this particular line. So we can say we want a line with a through point with this particular slope. So suppose we want a line through this particular point. This point P with slope 1. So this would be your unique line. So this one is unique. Line with this particular slope of 1 that passes through the point. But you see that there's infinitely many other points on like this particular line that would also be on the line, right? So there's other points that are also on the line, but this is just a way to represent this. And there's other lines too that are parallel to this particular line with the same, suppose it has the same slope. So let's find, the slope. There's a typo there. So slope. So find the slope of the line passing through the points 3, 5, and 1, 11. So let's do this. So 3, 5, and 1, 11. So this is our x1, y1. Let's pick it. This can be our x2, y2. Our points. So we're going to apply m equals y2 minus y1 divided by x2 minus x1 and calculate this. What do you get? So 11 minus 5 divided by x2, so 1 minus 3. I get 6 divided by -2, which is -3. So we see that the slope is, of course, here, -3. So we found the slope. What about if we switch these points? What would happen? So suppose, or what happens if we say, let's take the opposite points. Let's allow 1, 3 or 1, 11 to be equal to x1, y1. And 3, 5 to be equal to x2, y2. What happens now? Yes? For the second case, let's calculate it and see if you're right. See what the math tells you. Did you calculate it?
No, I didn't. I was just assuming.
Just, okay, just calculate, everyone, and tell me what you get. So we're just applying this definition. So we've switched it and we're seeing what happens. It's like an experiment here. So I just did it, and the slope was the same, actually. So the answer is, the slope is the same. So if we say, like, let's say we have 2 points and we're trying to find the slope between the 2 points. We can say x1, y1 is the first point, x2, y2 is the second point, or vice versa, and you get the same answer. So the answer doesn't depend on which points you choose as the first point or the second point. The slope is the same. So it doesn't matter. So it doesn't matter which one of the 2 points is x1, y1, and which is x2, y2. It does matter for perpendicular points and other things, but not this. And comparing it to something else. Sorry about this typo. So the equation of a line. So given its slope and 1 point on the line, if a line has the slope m, which we know, and goes through this particular point, let's call it point P at x1, y1, then this is the equation of the line. And we can actually derive this a little bit. So it's kind of interesting how to draw a sketch and understand this. Go back to blue. So the slope is m, and a point here is our x1, y1 point. So we can draw a sketch. Where am I going to draw it? Over here. So we have a point. And it's x1, y1. And this is an important kind of concept to really master, I think, just in general, like for math. And we have this line. So this is our line. Let's call it L. And we have this generic point, x, y over here. So this is a particular point. Let's write it down. Point on the line. And this is just a generic point on the line. So we can like derive this formula essentially. We know the definition of slope is basically, yes? Question?
If the points were reversed, say x1, y1 were on the prior point, would the formula still be the same?
Yeah. Yep. Yeah, it's the same. Yeah. Even if it's higher or lower. So this is just a generic point. This is a particular point, but it would work over here as well. And you can try it with like numbers and see what you get too. So the slope here is rise over run, which by definition is just the change in y. So that's the difference, y2 minus y1, divided by x2 minus x1. Now, y2 and x2, they're just generic points. because this is, I didn't have them x2, y2. We're saying they're generic. So we can like plug that in. So just say y minus y1. This is x minus x1. And now we can just rearrange and solve. So basically solve. So then m is going to be equal, so solve for basically y, this equation. And we have m is equal to this. I'm just copying it down again. No need to really. Which implies if we cross multiply, this is a trick, m times x minus x1 is equal to y minus y1. We can then therefore add y to both sides, get m times x minus x1 plus y, or let's add y1 equals y, because we're isolating here for y. So that's what we have right here. So same thing. So this implies our y is equal to our m times our x minus a point, our first point, plus our y1 point. So this essentially means that a point, I'll write it up here. Point x, y, that is on this line. It has to be on the line. Has to satisfy this. So that's point 1. Point 2. So any point xy point, sorry. XY that satisfies this equality will be on the line. So this was basically the equation of the line down here. So we just derived it and showed where it came from. So essentially, so this is the equation of the line, the y. We have our slope, x1 and y1 are points. And x and y just are generic points. And we can get the equation of the line for infinitely many lines. So we just showed that, sorry. So an example here. So consider a line with a slope of 4. And suppose it goes through a point. And let's say that point is like, let's say 3 and 5. So we have the slope and the point. Find the equation of this line. So this is a classical kind of example. Okay. So again, the point here is 3 and 5. And it's a particular point on the line. And we have our slope equals 4. It's always great to extract the information and write it down from the problem. Okay, so then y, of course, is equal to our formula, which we just shown. So we can substitute this in. So our slope equals 4. X here is just generic minus our particular point. So this is x1, y1. So x1 is 3 plus 5. And this is the equation of the line. If you wish, you could distribute the 4 in, so it's 4x minus, and then 4 times -3, so -12 plus 5. So you could group it together, but it's up to you. Now, we could check if we wish, or which color should we use? Running out of colors. Reflective. So if we wish, we could check. If a point is on this line. So let's check 6 and 10. Is this on the line? Anyone? So the idea is to check by saying like, so 10 over here, is that equal to 4 times 6 minus 3 plus 5? Question mark. Does this point like satisfy this equation? I see, no? Right, so like this is 10, and like this would be equal to calculate it 17. So no, right? So therefore, this point, 610, is not on the line. This equation. Y equals 4, x minus 3 plus 5. Okay. Yes?
If you were to ask us to find another point on the easiest way to say x equals 0.
Yeah. That's the next slide, y-intercepts and things like that. If that's where you're thinking, right? X equals 0 and then the y point. Yeah, that's actually, I think, yeah. See, y-intercepts. Yep. There we have it. That's true. So, yeah, it brings us to my next point. It's good when people are like thinking ahead of what's on the next slide or about to. Because it's, so the point where the line intercepts this y-axis, if it ever does, is called this y-intercept. If we know the y-intercept, we can use it to find a particular point on the line, exactly what he just asked. So this simplifies our formula. So the y-intercept of any line has this coordinate x1 is equal to 0 and y1 is equal to b for some b. So this is basically that y-intercept formula that you probably know. I hope so. So this would be 0 and b. Okay. So plugging in these values into our formula, you're going to see that this x1 is 0. So this is 0. This is our b, and you get mx plus b. So essentially, you can do this yourself. Write it out just to convince yourself. And then we see like this is equal to 0, this is equal to b. And we clearly see that m times x minus 0 plus our b. So this is just going to be mx plus b. So it implies y equals mx plus b. And we can, of course, draw a little sketch to understand this. So this would be where our b is. And this is our y-intercept. Which is our, of course, at the point, the pair 0b. So the y-intercept is the point. So it is a point on the line. Zero b, where this one was our x1 and this one was our y1. Those were the points. Okay, so a line, suppose we have a line and it contains these points 0, 4, and 2, 8. Find the slope of this line and then use the slope intercept form to find an equation of the line. So what we're doing is we're finding the slope, m, question mark, and we have like these particular points. So we apply the formula, which you're familiar now, slope. It's also change in y minus the change in x for the difference. Calculate this out. So we notice here, this point here is 0, 4. So that's our y-intercept. Oh my, so it gave it to us. So 0, 4. So because we have the slope and we have the y-intercept, we can just apply the formula. So this is then the slope intercept form. So this would be a point on this line L. We could call it L, like we could call Y L because it's a line with its coordinate. This x coordinate obviously is equal to 0. So it's the y-intercept. So linear functions. So a linear function is a function that represents basically a line. I know it's so repetitious here. So therefore, all linear functions have this form, y equals mx plus b, y equals to f of x. So we have f of x equals mx plus b, where x again is that input. For some numbers m, where the m is our slope, and b is that y-intercept. So this is again the same thing here. Sometimes we have to do simplifications to see this, that this function has this form. Sometimes you have to multiply things in, but we can see that. So essentially a linear function, let's just make a note so you see it. F of x is basically a function that can be expressed in this particular form. Again, this is the slope. And again, this is our y coordinate. Of the y-intercept. So if in a linear function, this slope is 0, so it's like it doesn't rise. As x changes, y doesn't change essentially. This means that y is not changing while you move along the x-axis. So what does like this function with m equals to 0 look like? So I'll draw it here. Sorry. So this is for over here. So such linear function when m equals 0 are called constant functions, and they're of this particular form. So when they're just equal, m is equal to 0, so m times x is 0. So the function is just equal to that constant b. So we can essentially draw the picture. So it's just going to be like this. That's what a constant function looks like. So this is f of x equals to b because f of x is equal to 0 times x plus b. And so therefore it's just equal to b. So therefore we see this is also a linear function. It's a straight line. It's the simplest case, but it's just a straight horizontal line is a constant function, and the slope here is 0. Because as you see, as x changes, y isn't changing at all. So if your slope were equal to 0, then the line has the same, basically, a y value, of course, everywhere. So it's just a horizontal line, as we can see. And this again is called this constant function. So this just means that f of x equals b is basically just known as the constant function. Now, so back to parallel lines. Remember that two lines are parallel if they have the same slope. So what does this mean? So just basically parallel implies same slope. And same slope means that the lines are parallel. So we could draw like a quick little sketch over here regarding point number 2. So all these lines basically parallel because all the lines have the same slope. So all these lines here have the same slope. So therefore, they are parallel lines. All these lines specifically are parallel. Okay. just as a reminder. So find the equation of a line that contains this point and it's parallel to this other line too that contains these 2 points. So we can quickly do this. So we have L1 is this particular point, 2 and 3. And we want L1 to be parallel. We use this notation to L2. And L2 is the points -1 and 0 and 2 and 1. So let's find the slope first. So that's part of find the slope of L2. So M2 is going to be just 1 minus 0 divided by 2 minus -1. Calculate this, get 1 over 3. So basically, since L1 is basically parallel to L2, L1 has the same slope. Okay. Because of this, just one more point. So now we know a point on L1 and the slope L2. Slope L1. So an equation for L1 is then as follows. So it's just going to be y equals m times x minus x1 plus y1. Got the slope, it's 1 over 3. We got our point. We plug in our point. And that's it. And for an exercise, graph these. So exercise, draw L1 and L2 to see if they have the same slope. And parallel.